Bismillahirrahmanirrahim. Assalamualaikum warahmatullah and a very good day to all students. The topic of this video is minor energy losses in pipes. Okay, as you already know, when we are dealing with energy losses in pipes, we have two types of energy losses. One is major energy losses, and the other one is minor energy losses. So minor energy losses can be due to sudden expansion of pipe, sudden contraction of pipe, bend in pipe, pipe fittings, or obstruction in pipes. So these are some of the examples. Okay. So minor losses. So one of the most important thing when we are dealing with minor losses is about this K. Okay, this K. So let's look. Okay, minor losses are proportional to the velocity head of the fluid as it flows through elbow, enlargement or contraction. So this is the formula for calculating HL. So HL is head loss, which is equals to K times V to the power of 2 divided by 2G. So this is the element of velocity head. So H loss is proportional to the velocity head. Okay, so experimental values for energy losses are usually reported in terms of a resistance or loss coefficient K as follows. Okay, so this K is representing the minor losses in pipe. So K is determined through experimental work. Okay. Okay, so now you can see here that there are 8 types of minor losses. Okay, so this is losses, not losses. Okay, sorry for that. Okay, for example, we have 1 to 8, sudden enlargement, gradual enlargement, sudden contraction, gradual contraction, entrance loss, exit loss, or resistance coefficient for valves and fittings or pipe bends. So all these 8 have different K, K, which are determined from experiments. Okay, so this is just an example of the picture. So for this elbow, we have like 3 different types of elbows, as you can see here. And this is sudden enlargement. So from small, it suddenly goes into big pipe. So there is loss of energy here. Okay. Okay, for sudden enlargement, as you know, this is how we calculate losses due to sudden enlargement, and the important thing here is K and also V. All right. Okay, you see this figure. As the water flow from the small pipe to the bigger pipe, you can see that we have different V here, we have different P, and we have different A. And as it flows into the bigger pipe, we will get different V, P, and A. Okay, and of course, here the diameter, which is also I mean the here the D will reflect in A, right? It's different from these two types of pipes. Okay, so here V1 is the average velocity of flow in the smaller pipe ahead of the enlargement. Okay, you know this. The value of the loss coefficient K is dependent on both the ratio of the size of the two pipes. Okay, as I said just now, the size of the two pipes, which is A1 and A2, and the magnitude of the flow velocity, which is V. Okay, of the flow stream, K can be predicted by this equation. So this is the equation to predict K. 1 minus A over A1 over A2 to the power of 2, which is equals to 1 minus ratio of D1 to D2 to the power of 2. All these are to the power of 2. Okay, so basically this is similar, except that this is A and this is D, but the ratio is similar. Okay, so you don't have to determine the A, you only have to know the diameter, and then you will use this equation to find K. Alright? Okay, so 1 and 2 indicate to smaller and larger section, as in this figure. This is figure 4.1 actually. Okay. Okay, values for K from this equation agree well with experimental data when the velocity v1 is approximately 1.2 meters square. So you can use this equation, and it agree with experimental data until the velocity is 1.2. I'm just repeating the sentence. Okay, so what is 1, 2, 3? 1, 2, 3, what is this? Let's see. Okay, so when you know already d1 and d2, so you have this ratio d2 to d1 ratio. So you have this value, and then you know the velocity, and then from there you can find the resistance coefficient. Okay, so this in these boxes, these are the resistance coefficient, or we can also call it as loss coefficient, which is K for this ratio of d2 over d1 and for this specific velocity. So you have this, you have to know this information. Okay, and this can also be known from this graph. So the engineers those days, so they did this experiment, and they have these two presentation. One is in table and the other one is in figure. Okay, so this is quite straightforward. Okay, just now we look at sudden. Okay, now we look at sudden enlargement. Okay, after this we are going to look at sudden enlargement, and after this we will look at gradual enlargement. Okay, so this is gradual enlargement. Of course, the formula for calculating H loss is similar except for the K that we have to find. Okay, in this situation, when it's gradual, so you have this element. The third element is the cone angle. Okay, so you have D1, you have D2, and you have the third element, cone angle. Okay, so the cone angle is either you have to measure or it's given by the manufacturer. Okay, for this case, it's the same. First, you are interested to find the K, right? So what must you know? You must know D2 over D1, and then you know the angle, and then you can find the K. So this is very straightforward. Okay, so this is the table and this is the graph. Sometimes you can look straightforward to the table, but when the values are not in the table, you can refer to the figure. Okay? Okay, so this is also sudden, no, this is a different topic. I mean different type of loss. This is sudden contraction. So it's just the opposite of sudden enlargement. With sudden contraction, you have a bigger pipe first, and then it flows into the smaller pipe. So of course, first you have to determine D1, and then you know D2, and then you know the velocity, and then you can find K. Similar, you can find K according to a table like this, and also from the figure. This is very straightforward. Okay, and also we can calculate K for sudden contraction by using this formula. Okay, in this figure you have 0.1, 0.2 with this at the contraction here, and also you have the third point, okay, which is this is the second point. And from continuity equation, you know that Q at C is similar to Q at 2. So that's why we have this equation AC and times VC is equals to A2 times V2. So from here, the equation becomes like this, and it gives us this constant. Okay, so you rearrange this equation in this formula. This is also the formula for calculating the H loss actually. And then you can finally, by putting this equation earlier, 1 over C, this is the constant. So you will get this equation. And finally, this is K. If you want to find, if you don't want to use the table or you don't want to use the figure, you can also use this equation to find K. Alright? Okay. But here the thing is that you must know the velocity here. Okay. Okay. Let's see. Okay, this is for gradual contraction. So if you want to differentiate between sudden and gradual contraction, for sudden contraction, we don't have the third element. But for gradual contraction, we have this third element, which is theta, the angle of the cone. Okay, you have D1, D2, and the cone. Okay, so of course, it's similar. This is for the cone from 15 to 150 degree. This is a wide range of cone degree. Okay, so first you have D1 over D2. Okay, so we have this angle, and you can find K. Very straightforward, right? So this is the same, but this is for the angle below 15 degree. Okay, as the cone angle of the contraction decreases below 15 degree, the resistance coefficient increases. Okay, so you can observe this. Alright, so this is for entrance loss. So when the water comes from a big tank, a big reservoir into this pipe, there is loss here. So the K can be determined by looking at this shape. This is like inward perfecting pipe. So the K is 1. If you have square H inlet, the K is 0.5. So once you have this K, you just plug it into this equation and you can get the head loss for this type of entrance loss. Okay, so you also have like chamfered inlet and you also have rounded inlet. So for rounded inlet, you have to know how to calculate the R. Okay, but it's not given in this lecture. I will give it to you later. Okay, so for exit loss, when this kind of loss happen, so when the flow from pipe goes into a reservoir, so there is loss here. So in this kind of situation, the value of K1, K is equals to 1 is used regardless of the form of the exit where the pipe connects to the wall. So it's always 1. The K is always 1 in this kind of exit loss. Okay? Regardless of the form. Okay, now this is the resistance coefficient. So resistance coefficient is K for valve and fittings. So you have many different types of valves and fitting. These are flow through run. This is flow through branch. Okay, so the formula is slightly different at this case. So you have another element which is Ft. So for this one, K is equals to 20 Ft. For this flow through branch, the K is equals to 60 Ft. And for different types of bands, like this is 90 degree elbow, 90 degree long radius elbow, 5 degree elbow, and so on. So you have different formula for calculating K. So we just use this formula according to the type of elbow you have. Okay, as you know, the formula is always like Ft. So, and then you have to find LE over D. So it will be given to you according to the type of valves or fitting that you have. You don't worry, okay? So once you have the Ft from the nominal pipe size, okay, pipe size, okay, this is according to your pipe size. So you can get Ft, and then depending on the valve and fittings that you have, this is the LE over D. So once you have Ft and LE over D, you can find the K, right? Okay, so this is another type, another presentation. So this is more or less very similar, but sometimes some of the point here is not in the previous table, so you can always look at this table as well when you try to solve problems related to minor loss coefficient. Okay, this is also the same for different type of losses. And finally, we have example 1. So we will do this together in the next video. Thank you.